Hello students, today in this fourth video we are going to start a new topic, that is phosphorescence. Last time, if you remember, we have studied vibrational energy levels of a diatomic molecule. Then we also studied vibrational spectra and vibrational rotational energy levels of a diatomic molecule. And we have studied a very important effect in case of a molecule, uh, molecular spectra, that is known as a fluorescence. So these three topics we have learned in the last video. Now today in this video, one more very important effect in molecular spectra, which is known as phosphorescence. So we are going to learn what is this phosphorescence, and that is the actual last topic in this chapter. And after that, we are going to solve some of the numericals based on the topics in this chapter. So let us begin with the topic, that is phosphorescence. Now, last time we have studied one of the important effect, fluorescence, where we have studied that when the molecule from its ground state, when is excited to the higher level, that means the excited state in one of the vibrational level, where it performs certain collisions with the other molecule and lose a small amount of energy. So it will perform a downward transition to other energy levels, which are radiationless transitions, and then it will perform the reverse transition from excited state to ground state, uh, from the downward vibrational level as compared to the initial higher vibrational level. So initial absorbed photon, and finally during reverse transition the photon emitted, if you compare the energy, definitely the photon which is emitted later in the reverse transition has less energy, that means less frequency. So this effect is known as fluorescence. Now what is phosphorescence? Actually it is slightly different than fluorescence. The phenomena is same. So in phosphorescence, you can say it is a process in which energy absorbed by a substance is relatively released relatively slowly in the form of light. So in fluorescence, we have seen the energy initially absorbed for the excitation from ground state to excited state of the molecule. It is re-emitted during the reverse transition instantaneously, almost instantaneously. That time period is very small. But whereas in fluorescence, this phenomena is very slower. Okay, and that depend upon the type of molecule. For some molecule, it may be few seconds, microseconds. For some molecules, it may be hours, few hours also. So, unlike fluorescence, you can say a fluorescent material does not immediately re-emit the radiation which it has absorbed. So, in case of phosphorescence, the electron which is absorbed or which absorb the photon energy, it undergoes an unusual intersystem crossing into an energy state of different spin multiplicity. So, what does it mean? That means once the electron from the molecule is excited from the ground state to excited state. So you know that the molecule has certain spin multiplicity. For example, in singlet, you know that multiplicity S is equal to 0, and uh, that means the spin quantum number S is equal to 0. Okay, so multiplicity is actually 1. Whereas in triplet state, the spin quantum number is S is equal to 1, therefore multiplicity is 3, and therefore we call it as a triplet state. So what happens here in case of phosphorescence, when the molecule is excited from the ground state where it was in singlet state to the excited state where it is also in singlet state. But during the downward transition, when the collisions with other molecule takes place, it comes down to another vibrational level. But during this process, if the energy of the vibrational level of singlet state matches with the triplet state, there may be unusual inter-system crossing into an energy state of different state, spin multiplicity. That means from singlet state to triplet state. And now what will happen? It cannot perform the reverse transition because right now it will be in triplet state and its ground state is singlet state. So you know that the triplet to singlet, quantum mechanically this transition is forbidden and it will be trapped. So that transition will not be performed. That means energy absorbed by the molecule will not be released in the downward transition immediately. So quantum mechanically, even though it is forbidden, but it will take certain time and it will release the energy. So this phenomena is phosphorescence. So the forbidden energy state transition in quantum mechanics does not allow instantaneous re-emission. As these transitions occur very slowly in certain material, absorbed radiation is re-emitted at a lower intensity for up to several hours after the original excitation. So it will take certain amount of time. Let us try to understand this phosphorescence, how one can explain with the help of this particular diagram. So see, this is the ground state, singlet ground state of the molecule. Suppose a photon comes to this molecule and it will be excited to the singlet excited state, this red one, you can see this, or this red brown one. Okay, so it will go to one of the vibrational level in the singlet excited state. So this is the excited state of the molecule because of absorption of the photon. So it will go from singlet ground state to this singlet excited state in one of the vibrational level. Now what happened? The molecule in this particular excited state performs certain collision with the other molecule and it may undergo radiationless transition to lower vibrational level. You can see the arrows are shown here. So in the excited state, initially it was in this vibrational level, but because of collision, it will lose certain amount of energy, small amount of energy, and it will perform reverse transition to lower vibrational level. It's like this. This is first transition, this is second transition, and so on. But in this process, suppose the energy of the vibrational level in singlet excited state matches with the energy of the triplet excited state. This blue one I have represented by these blue lines. This is the triplet excited state. So these are the vibrational levels in triplet excited state. Now what happens during the downward transition because of collision of this molecule in the reverse direction? Suppose the vibrational level in singlet excited state has the same amount of energy in that of triplet excited state. So what will happen? There may be probability that there is a intercrossing from singlet excited state to triplet excited state. You can see over here. So the blue arrow, it is now crossed. It has crossed the singlet excited state to triplet excited state. And further again, few collisions, it will bring down to certain lower vibrational level. But what will happen now? So during the transition to lower vibrational level, if the energy of the singlet level matches with the energy of the triplet level, there is a probability of shifting the transition. Okay, triplet state, singlet state to triplet state. Okay, now in this process, the molecule is trapped in such a state where quantum mechanically the reverse transition between different spin state is forbidden. Because here triplet state, you know that S is equal to 1 and this is the ground state which is singlet state. So S is equal to 0. So spin quantum numbers are different. Therefore, this transition is not allowed quantum mechanically. So you can see here this transition, even though arrow is shown, but this is forbidden. Forbidden means it is not allowed. So quantum mechanically this is not allowed. So molecule is trapped in the excited state. So it will not emit the energy instantaneously. But kinetically it will lose the energy and that process will be very smaller. So it will, in some cases, it may take few minutes, few hours also. Okay. So this is the phenomena what is known as phosphorescence. So there are several examples we observe the application. For example, several stickers, especially from the backside of vehicles for safety purposes, when the light of another vehicle falls on the sticker, that they will glow and the glow continue several minutes. Okay. For example, some paints, there are paints of the you can say the boards indicating directions and all that. So during night also these paints can easily glow. So glow in dark, that is the characteristics of these paints. So the minute hand and hour hand of wristwatches and their dials also glow. These are few examples. Now the materials which are actually mostly used as a phosphorescence materials, they include zinc sulfide and strontium aluminate. These are the two commonly used materials. So this is what phosphorescence. So we have completed this particular chapter here. So what we have studied in this particular chapter is what is actually molecular spectra. Then we have studied about the different types of molecular spectra. Then the rotational spectra, we have considered the example of diatomic molecule. So we have defined the rotational energy level and we have studied the rotational spectra also. Then the second type, that is the vibrational spectra, vibrational energy level, also we have studied for a diatomic molecule, and we have seen two very important effects in molecular spectroscopy, that is fluorescence and phosphorescence. Now, further few numericals I am going to discuss here in this particular video. The first numerical, let us see now here. So the problem is, if the spacing between the vibrational level of carbon monoxide molecule is 0.08 electron volt. So this is the spacing given between the vibrational level. Okay. So calculate the value of force constant for the CO molecule. Given mass of carbon atom is equal to 12 and that of the oxygen atom is equal to 6 times the mass of proton, and mass of proton is given to you, that is 1.67 into 10 raised to minus 27 kg. Okay, so what is given to us? The spacing or energy difference between the vibrational level of carbon monoxide molecule, that is given to us 0.08 electron volt, and you are asked to find out force constant K. Okay, so how to solve this problem? So first of all, you know that in order to find out the force constant, first of all we will have to calculate the reduced mass of the carbon monoxide molecule and reduced mass. The two atoms, carbon and oxygen, they are involved in CO molecule, and they are 12 having mass 12 times and 16 times respectively of the proton mass. So mu is equal to m1 m2 upon m1 plus m2. This is the formula to find out the reduced mass of carbon monoxide molecule. So m is equal to 12 and m1 is equal to 12 and m2 is equal to 16. But it should be multiplied by a proton mass. Okay, because both of them, they are this proton mass times 12 times proton mass and 16 times proton mass. We have taken actually this common, because here also we are multiplying by 1.67 into 10 raised to minus 27, that is proton mass. So m1 plus m2. So if you have this, this will be 1.67 into 10 raised to minus 27 bracket square, and here single 1.67 into 10 raised to minus 27. So one of them will get cancelled. So only a single 1.67 into 10 raised to minus 27 will remain here. And if you calculate this will come to be 1.14 into 10 raised to minus 26 kg. So this is the reduced mass of the carbon monoxide molecule. Now we want to find out the force constant. For that we will have to use this formula. Now you know that if you assume a transition between two levels, vibrational levels of carbon monoxide molecule, then energy difference delta E will be given out. That will be energy difference of the two levels. For example, the first level, so E having vibrational quantum number V plus 1 minus EV. These are the two adjacent vibrational level. So the difference in energy, that is delta E, that is equal to h nu 0. And nu 0 is the classical frequency of vibration of this carbon monoxide molecule. And that is given by nu 0, you know that 1 upon 2 pi under root of K upon mu. So this will become h upon 2 pi, because we are multiplying by h. So delta E is equal to h upon 2 pi under root k upon mu, where k is a force constant which we want to calculate and mu is the reduced mass of this carbon monoxide molecule. So we have just calculated this reduced mass. We want to calculate k. H is Planck's constant. You know its value 6.63 into 10 to minus 31. So everything is constant here, and the energy difference between these two levels delta E is given to us, that is 0.08 electron volt. So you can substitute here and you can find out the equation for K. How? So delta E is equal to, if you square this, if you take a square of these both sides, so this will be what will be that? Simply h square nu 0 square, that is equal to h square upon 4 pi square into k upon mu. And if you solve this equation for this, so therefore here k upon mu, that it will be equal to 4 pi square upon h square, 4 pi square upon h square into delta E. Okay, so therefore here this k, that is equal to 4 pi square. So let us now calculate the formula. 4 pi square upon h square. So the mu will be on this side, mu will be on this side. So k is equal to 4 pi square upon h square mu into delta E. Okay. So this is the formula for k. Just substitute the values. So what will be that? Delta E is equal to 0.08 into CR. This delta E, we want to convert it to joule first because it is in electron volt. So we have to multiply by 1.67 into 10 raised to minus 19. So H value here is Planck's constant in this particular case. This is the H we want to substitute here. So just substitute these two values, delta E and H. So using the values in the equation for K and this delta E, we have substituted this value, H we have substituted this value, and if you perform the calculations, K will be 167.8 Newton per meter. So in this way you can calculate the force constant for carbon monoxide molecule. Now let us go to one more numerical second problem. For carbon monoxide molecule, J is equal to 1 to J is, J is equal to 0 to J is equal to 1 absorption line occurs at frequency 1.15 into 10 raised to 11 hertz. What is the bond length of carbon monoxide molecule? The reduced mass of the molecule is given here, 1.14 into 10 raised to minus 26 kg. So what we want to find out is the bond length. So if you remember, while studying the vibrational energy level, the bond length, that is the distance between the two atoms, that is carbon and oxygen, that is the bond length, and it is R0. So the equation for R0 we have to use here, and that we have to solve to find out the bond length here. Okay, so what is given here is for the carbon monoxide molecule, the transition, the rotational energy level, quantum number J is equal to 0 to J is equal to 1. The absorption line has the frequency 1.15 into 10 raised to 11 hertz. So the absorption line for this transition is given. This is the rotational transition specified here for carbon monoxide molecule. So you know that the rotational energy Ej is equal to h square upon 8 pi square I into J in bracket J plus 1, where J is the rotational quantum number, I is the moment of inertia, and H is the Planck's constant. So if you consider for J is equal to 1 and J is equal to 0 and take the difference, that will be delta E. Okay, the difference between these two transitions, and that energy is absorbed in the form of this radiation having frequency 1.15 into 10 raised to 11 hertz, and you can equate that energy delta E, that is equal to h nu, where nu is this frequency. Okay, so Ej is equal to 1 minus Ej is equal to 0. This transition energy, that is delta E, that is equal to the, if you substitute J is equal to 1 here, what will be that? 1 in bracket 1 plus 1, that is twice of this. So twice of h square upon 8 pi square I minus Ej is equal to 0. If you substitute J is equal to 0, this term will be 0 and this will be 0. So this will be 0. Simply delta is equal to 2 h square upon 8 pi square I. Okay, so therefore you know that delta E is equal to h nu, and h is Planck's constant, nu is the frequency which is given to us. So you can substitute delta is equal to h nu here. H nu is equal to twice of h square upon 8 pi square I. So nu is equal to h, you can take to the right hand side. So one of the h will get cancelled. So nu is equal to h upon 4 pi square I. So these two fours are 8. So this will become 4 here. So one of the h will get cancelled. So we nu is equal to h upon 4 pi square I. But I is equal to mu r0 square. If you remember, the uh, diatomic molecule has the moment of inertia I is equal to mu r0 square, where mu is the reduced mass and r0 is the bond length, okay, distance between the two atoms. So the reduced mass is given to us, so we can substitute mu, and the moment of inertia uh, for this particular diatomic molecule, you can just substitute this mu r0 square, okay, in this formula. I is equal to mu r0 square. So mu is equal to, now if you remember, this formula we are using now, okay, this mu is equal to h upon 4 pi square I. So I, we have to substitute as mu r0 square, okay. So this is mu r0 square. So let us rearrange the term because we want to find out r0, that is bond length. So r0 square you can take on this side, mu on this side. So r0 square is equal to h upon 4 pi square mu into nu. And let us now substitute the values. So r0 is equal to, h is Planck's constant having the value 6.63 into 10 raised to minus 34 joule second. Then 4 pi square, 4 into 3.14 square into this mu reduced mass, which is given to us 1.14 into 10 raised to minus 26 into the frequency, that is 1.15 into 10 raised to 11. So this should be raised to 11. Okay, this it has appears as 11 simply, but it should be 10 raised to 11. Remember. Okay, so if you substitute this and if you calculate all these, so that will be the bond length R0 will be equal to 0.113 nanometer. So this way you can solve any kind of problem if you know the vibrational energy level formulas and the rotational energy level formulas for diatomic molecules specifically, which we have studied in this chapter. So that is the end of this particular chapter, that is sixth chapter we have finished here. And in the next video, I am going to start the seventh and last chapter, that is Raman spectroscopy.